Okay, great. So far, we've explored AI basics, its history, and the distinctions between weak and strong AI. You already learned about the key ingredient to building AI: high-quality, abundant data. We're making excellent progress. Next, we should explore machine learning, the AI subfield pivotal to its recent success. The idea of ML is fascinating because it boils down to designing a system capable of learning and improving through a trial and error process. Consider building a machine learning model similar to a student taught by a teacher. In this case, the machine learning model is the student, and the data scientist is the teacher. The teacher's role is to help the student learn how to solve problems. To do this well, the teacher must provide the student with many suitable learning materials, which in the world of machine learning means providing a lot of good data. With sufficient information, the student carefully studies and absorbs the training materials. Similarly, the machine learning algorithm learns to recognize patterns in the fed training data. The aim is to prepare students to succeed on their final exam, featuring unfamiliar questions that test previously covered material. In the ML model's case, we aim to teach it how to solve a particular problem with data it has never seen. The more up-to-date and better the training data, the better the model can solve new, challenging problems it has never seen. Without adequate training, a student may underperform compared to a well-taught one, regardless of natural talent. The same goes for machine learning. A simple model with lots of good data might do better than a more complicated one with less data. Adopting new teaching methods and tailoring styles to students can significantly enhance their performance. Similarly, in machine learning, models improve prediction and analysis as they encounter new data types and updated algorithms. This continuous learning and adaptation process is crucial to developing robust AI systems that can handle diverse challenges and evolve. Just as some students excel in problem-solving across various fields, certain ML models are better suited to specific ones. The data scientist needs to understand this and be able to use the appropriate ML model in a given situation. I hope this somewhat abstract example was helpful. Let's give a more practical example of how ML can help businesses. A real estate agent plans to develop a mobile app to provide prospective clients with an estimated selling price for their homes. Users can receive this estimate by answering targeted questions within the app. This could significantly boost the real estate agent's business by enabling them to collect contact details from people interested in selling their property. To put the plan in motion, the real estate agent contacted a data scientist and asked whether the project was feasible. The data scientist's first question regarded the availability of a sufficiently large list of past transactions. Fortunately, the real estate agent's company had access to a database with thousands of past transactions over the last few years. Later, the data scientist was pleased to find the data well organized, detailing house prices, sizes, room counts, bedroom numbers, distances from the city center, neighborhoods, and other fascinating aspects. "I can build an ML model with that," said the data scientist. Here's how the data scientist simplified the model for his client. You're familiar with the classic function notation where y is a function of x, right? Imagine we want to develop a machine learning model to predict house prices in our city by analyzing past real estate transactions in your training dataset. So, we have plenty of past transactions where both x and y are known. We need to train a machine learning algorithm with historical data to discover patterns and learn the best way to predict the future price of a home, y, based on the data from past transactions and the home's known characteristics. Clients enter their home's characteristics into the app. This forms input x. The ML model then generates output y, predicting the home's price based on similar historical data. This is where we'll end the story. Spoiler alert, the app was a huge success for the real estate agent's business. I hope this lesson clarified what machine learning is and how it works. In our next lesson, we'll discuss the different types of machine learning models. Thanks for watching. In this video, we'll describe 3 main types of machine learning: supervised, unsupervised, and reinforcement learning. Then, in the next one, we'll explore deep learning, a sophisticated subset of machine learning powered by neural networks and inspired by the human brain. If this sounds too abstract and complicated, please don't worry. We'll talk about the intuition of these AI techniques without getting into too much detail. Supervised learning excels when we work with labeled data. In the earlier example, the training data set reveals whether a picture contains a dog. This is how the algorithm can learn to classify new pictures as dog or not dog. We've provided the ML model with an extensive training data set with labeled data, and it knows what to look for. Later, when we provide a new picture, it can identify whether it contains a dog based on the feedback given during training. This is a classification problem solved by supervised ML. The other primary application of supervised learning is predicting an outcome. Remember when we discussed the real estate agent's mobile app in our last lesson? Well, the dataset with past house sales transactions contained both known prices and features of the homes. We didn't merely highlight home features. This is an example of supervised learning too, but it's used for prediction, also called a regression problem. When a user inputs the characteristics of a new home into the app predicts the new home's price based on its features and historical information for similar homes. So, simply put, in supervised learning, we explicitly train the model with known outputs to guide its learning. In unsupervised learning, we process data without labels. For example, in a data set of 10,000 animal pictures, half feature dogs, and the other half various animals. But we provide the machine learning model with no labels or indications. It will need to scan through all pictures and look for patterns. Ultimately, it will be able to distinguish specific groups and individuate them. We'll have a group of dogs, a group of cats, and so on. The ML model, however, doesn't specify the contents of these images. It merely indicates that they share similar characteristics, grouping them. Unsupervised learning is helpful in many situations. First, labeling data is costly and not always practical. Moreover, sometimes we don't know what relationships we should look for in the data, so it makes sense to have the algorithm find these interesting relationships first. In this way, a supermarket chain could find clusters of target customers with different behaviors. Or a real estate agent could use an unsupervised model to determine which types of properties are sold most often. Another key ML type is reinforcement learning, which operates without labeled data and is applied in specific scenarios where the machine figures out how to reach a designated goal. Reinforcement learning shares with supervised ML the understanding of the desired output. We essentially direct the computer to optimize our goal achievement. But unlike supervised learning, we don't provide labeled data to the ML model. Instead, we create rules. The ML model learns through trial and error within specific parameters of our created rules. Reinforcement learning thrives in robotics and online recommendation systems. For example, platforms like Netflix use reinforcement learning to enhance recommendation systems. Unlike traditional methods that rely on labeled data, which indicates which TV shows a user might like, reinforcement learning employs a system where the model learns from user feedback through interactions. Initially, Netflix may provide random show recommendations. As a user interacts with these suggestions by watching a show, adding it to their list, or skipping it, the system gathers feedback. Positive interactions, like watching a full episode, signal the model to recommend similar content in the future, while negative responses, like skipping a show, guide it to adjust recommendations. Over time, the model refines its predictions to better align with individual user preferences, constantly adapting to new viewing patterns and behaviors. Alright, so that's the intuition behind supervised, unsupervised, and reinforcement learning. In the next lesson, we'll examine deep learning, a truly fascinating feat of computer science. Deep learning is a fascinating subset of machine learning, inspired by how the human brain works. Here's an AI-generated image. What do you see at first glance? It's a sunny day and a crowded beach, right? Upon closer inspection, we see children playing in the sand around a massive sand castle at the center. We then examine each person on the beach more closely. We find that AI rendered this individual's face oddly, resulting in a bizarre and slightly unsettling appearance. Our brain processes information in various phases and at varying depths. Initially, viewing an image provides a raw, broad impression that presents insights into the scene's context. The more time and attention we devote to details, the more information and subtleties we can process and observe. In the context of deep learning, a neural network processes information similarly. Here's what a neural network resembles. Please don't be scared. Everything will make sense in a second. Picture the first layer as our input information, similar to observing a sunny, crowded beach day. Then, as the data passes through more network layers, intermediate layers start recognizing more complex features, such as shapes or specific objects. Remember how I noticed the enormous sand castle in the middle? Every intermediate layer of the neural network builds a more detailed understanding of the basic features identified by earlier layers. So there's an incremental increase in the level of detail acquired. The deeper layers of the network synthesize lower-level features into high-level features, representing more complex aspects of the input data. This is how we can spot the strange face generated by AI. It took some time to process the information and get to this conclusion. Honestly, I think I subconsciously wanted the picture to reflect that, because I was curious if the AI had produced a quality example. And eventually, my brain focused on this little detail. Okay, perfect. So that's the intuition behind deep learning. It's a complex process that allows machines to learn by processing input information in stages. Let's explore some technical details to deepen our understanding. We call this neural network Artificial Neural Network, or ANN. Biological neural networks inspire it, but they work much differently. Like our senses, an ANN's input layer sends raw data to the brain. Then the intermediate layers, or hidden layers, process input information. Neural networks can have one or multiple hidden layers. Increasing layers enhances complexity. Adding more layers to a network increases its learning capacity, but the downside is that it needs to be carefully managed to ensure effective learning. We also have an output layer that generates the final result. Every layer of the artificial neural net is made of neurons, or nodes, responsible for processing and transforming the information received. If you recall, I previously referenced the MNIST example in one of our lessons. We noted that training a model to recognize handwritten digits involves supplying it with thousands of pre-labeled examples. How does this training happen? While the process may initially appear complex, let's simplify it to a more manageable form. The process starts with the input layer of the ANN receiving an image of a handwritten digit. Each pixel of this image serves as an input node. In the case of MNIST, images are 28 by 28 pixels, so the input layer typically has 784 input nodes. Imagine that the 784 input nodes are stored as a vector inside the neural net to form the input layer. Each of the 784 input nodes contains a number based on how bright or dark it is. Here, 0 represents white, while any value greater than 0 indicates a color other than white. We call this number activation. The higher the number, the darker the content inside a given node. We describe the 784 input nodes in the input layer as the neural net's width and its number of layers as its depth. Here, the network comprises 3 hidden layers along with the input and output layers, totaling a depth of 5. We have numerous connections between nodes because each layer's nodes are linked to every node in the subsequent layer. This extensive network of connections is essential for learning from input data, serving as mathematical transformations. These transformations occur through a mix of weights and nonlinear operations, with optimal weight combinations across all nodes enabling learning. This method translates the input via various layers, refining the information before it generates a result. Learning occurs by designing a system that identifies optimal weights and biases to solve a specific problem, involving thousands of repetitions to discover the best combination. So, why do we need several layers? What kind of transformations can we expect in each layer to end up with a system capable of recognizing the digits in a photo? Well, when we see an image in the background, our brain connects various components of what it is made of. For instance, the number 3 comprises 2 elements, a rounded top and a curved bottom. The first hidden layer in our neural network might learn to recognize these features from the input data. Then, in the second hidden layer, we continue to build on the information processed by the previous one. We've identified edges and curves, and now we can use them to discern more complex shapes, like loops and intersections, bringing us closer to recognizing numerals. When the information reaches the third layer, the neural network has learned to recognize the overall shape and configuration representing the number 3. Finally, the output layer takes the processed data from the last hidden layer and determines whether the digit is a 3. This is how a neural network learns to perform what appears to be a simple task, recognizing a number. The underlying process, however, involves intricate mathematical manipulations, which we didn't describe fully. In essence, the layers of an ANN, through their depth and breadth, create a robust system of pattern recognition and data interpretation that mirrors some aspects of human cognitive processes, albeit more structured. This capability to analyze large, high-dimensional data sets and recognize complex patterns with high accuracy makes deep learning a revolutionary tool in AI. It's what has made today's incredible AI advancement possible.